So what I wanted to talk about today is something I've been thinking about quite a lot lately, and that's pipelines. And I'm interested particularly in data analysis, which to me is the process where data comes in one side, understanding, insight, knowledge, and action come out the other. And to me, there really are five main sets of tools you use to do data analysis. So first of all, you need to get your data into your data analysis system of choice. Now, for me, obviously, that's R, but I think these ideas apply regardless of what tool you're using, whether it's SAS or Python or something else. I think it's useful to frame your analysis in this way because it helps you kind of understand the strengths and weaknesses of different systems. So first of all, you need to get your data into R, you need to import it, and then once you've done that, I think it's really useful to tidy your data. And I'll talk more about exactly what I mean by that later on. But basically, tidy data is just a consistent way of storing data. And if you have a consistent way of storing data, then your life is much, much easier because your tools get easier. You're not constantly fighting your tools to do what you want. The data just stays in one format and every function knows how to work with it. Now, typically the first thing you'll do once you've got your data into R in a tidy format, you'll start by doing some transformations. That's things like creating new variables that are functions of existing variables, or maybe aggregating or sorting your data. And then there really, to me, are two main engines of insight discovery: visualization and modeling. Visualizations are great because they can surprise you. You can see something you fundamentally did not expect in a plot. Visualizations can also be really useful at helping you refine your questions. And I think, often a big part of the challenge of a data analysis is just taking that vague, ill-formed question in your head and making it sufficiently precise that you can answer it quantitatively with data. Now, the problem, however, with visualizations is that they're fundamentally aimed at humans. Two eyeballs and a brain has to look at every visualization. So that means visualizations fundamentally don't scale. So to me, the complementary tool to visualization is modeling. And I think of modeling very broadly. This is traditional statistical modeling, this is machine learning, this is data mining. But basically, whenever you can make a question sufficiently precise, you can answer it with some numbers or an algorithm. I think of that as a model. Now, models are great because they're sort of fundamentally a computer-based activity, and that means they scale much better than visualizations. And even if a particular model doesn't scale that well, it's always easier to throw more computers at a problem than it is to throw more brains at a problem. The problem with models, however, is that every model makes assumptions that by its very nature cannot question. So models scale really well, but they can't fundamentally surprise you. A linear model is never going to tell you its data is actually nonlinear. So that's why I think visualization and modeling are really, really complementary tools. Visualizations surprise you, but they don't scale. Models scale, but they can't fundamentally surprise you. Now, over the last few years, I've spent a lot of my time trying to make packages to make these parts of the process, of the data analysis process, easier. Now, I'm not going to talk much today about the import process, basically because that is incredibly boring. And these packages are designed to be incredibly boring, right? They're just designed to work. You point them in a data source and you get a data frame back. So there's readr for reading in flat files, readxl for reading in XLS and XLSX files, Haven for reading in files from other statistical packages like SPSS, Stata, and SAS, DBI for talking to databases, and HTTR for talking to web APIs. Once you've got, so these packages basically give you a data frame. Then I really strongly recommend that you use the tidyr package to get those data frames into a tidy format. Again, I'll talk about what that means in a little bit. Talk about using the dplyr package to do data transformation. We'll talk about mostly about ggvis for visualization. You're probably more familiar with ggplot2. ggplot2 is currently, I'd say, like the tool of choice for production. It's really solid. Hundreds of thousands of people have used it. It's very featureful. ggvis, however, it's still very young. I'm going to show you. I think it's really exciting, but it still lacks a lot of the features that you need from ggplot2. I'm putting a lot of my time now into ggvis rather than ggplot2. So I want to show you kind of where I think the future of visualization is now. Now, I'm not going to talk much about modeling, but I do want to talk a little bit about the Broom package by David Robinson, because that really facilitates the connection between models and visualizations. Now, all of these tools I'm going to talk about are unified by the idea of a pipeline. And this work is really inspired by my kind of mental model of the cost of the data analysis process. And I think first of all, when you're doing a data analysis problem, you have to think, what should you do to solve this data analysis problem? Then you need to describe that precisely in such a way that the computer can understand it. In other words, you need to program it, and then the computer needs to go away and actually do it. And in my experience, most of the time, most problems, it's the thinking time that's the bottleneck. It takes you much, much longer to figure out what you want to do. And then once you figure that out, it's relatively straightforward for the computer to go away and do that. Now, I think there's sort of one area where this is not true, and I think this sort of makes an interesting definition of big data, and that's big data is where computation time is now the bottleneck. Now, even when you've figured out what you should do, it's going to take a long time to actually go away and do it. I'll talk a little bit about big data near the end of this talk. So I'm going to be talking about this pipe operator from the Margherita package. Now, the idea of piping is a very, very old one. It comes, Unix has the idea of pipes. Lots of other programming languages, functional programming languages in particular, like F# and Haskell and Clojure, have similar things. And then the idea of method chaining in Python and JavaScript is very similar. So the idea of piping itself is not new. It's a very old and useful idea. But this instantiation in R through the Margherita package is quite useful. And I'm going to illustrate this, the pipe, with a little story about a bunny called Fufu. Now, if we tell the story about Fufu, so Fufu hops through the forest, scoops up a field mouse, and then bops it on the head, kind of function calls, it's a little hard to read. Backwards from inside out, from right to left, which is a little awkward if you're an English speaker. The problem is the arguments of the functions tend to get rather spread apart, which makes it hard. Now, that's annoying because it makes our code hard to read, but functions are really, really nice because they make our code much easier to reason about. And so what this pipe operator from the Margherita package does is it allows us to write code that's exactly equivalent. And in fact, it's transformed internally in R to exactly this code, but now we can read it as if it's a sequence of operations. So little bunny Fufu hops through the forest, then scoops up a field mouse, then bops on the head. And I think a really natural way to pronounce this operator is as then, because we're doing this sequence of transformations. Now let's look at this a little more formally. So basically what happens when you say x, then f of y, we do this transformation where the thing on the left-hand side becomes the first argument on the right-hand side. Now we can, of course, override that, so we can pass the thing on the left-hand side to the second position if we use this, this pronoun, the dot, or we can chain multiple functions together. And the goal here, the idea of this is it turns function composition, which is hard to read, but easy to reason about and easy to program, into a sequence of imperative operations that's really easy to read. And I think that's really important because code is a medium of communication. It's obviously a medium of communication between you and the computer, but less obviously, it's also a medium of communication between you and other people. And it's really important to realize that every project you work on always has at least two people. You always have at least one collaborator, and that's future you. And if you're anything like me, when you come to a project that you worked on like 3 months ago or 6 months ago, often you'll look at it and it's like a complete stranger wrote it. And not just a complete stranger, but a complete stranger who might possibly be quite insane. So I often have this experience of like looking at code that I wrote 3 months or 6 months ago. I have no recollection of writing it, and I have basically no understanding of what it actually does. So focusing on code as communication, I think, is really, really important. If you can write code today that is clear and easy to understand, it's going to be much, much easier for your collaborators, including future you, to understand what's going on and understand, not just rerun code, which is obviously really important, but to also kind of re-understand why you were doing what you were doing. So I'm going to show you a few examples of pipelines today. The cool thing about this pipeline operator is any function can use it. It doesn't need any special properties of that function. I'm going to show you a few examples. TidyR, which takes messy data and makes it progressively more tidy. dplyr, which provides pipelines for manipulating data. ggviz for doing pipelines of visualization. But there are lots of other ones for scraping HTML, manipulating lists, working with XML and strings and so on. So let's start by talking about tidy data with the TidyR package. And the goal here is really simple. The goal is to store your data in a way that makes the rest of your analysis as easy as possible. And what this means in practice is you want to match the statistical structure of your data with the physical structure. And I think the best way to do that is to make sure each row is an observation and each column is a variable. So let's take a little look at a little example of that, and I'm going to give you guys a little challenge. So here's some data about tuberculosis rates collected by the World Health Organization. So what I want you to do, if you're sitting by yourself, think about it. If you're sitting with someone else, talk with them. I want you to figure out what are the variables in this data set. Now I'm going to give you one hint. That is that F stands for female and U stands for unknown, and that 1524 stands for 15 to 24. So I'm going to give you guys a minute. I'm not going to say anything because I want you to think about this for a few seconds. What are the variables in this data set? Okay, well, hopefully you all spotted that year is a variable. And some of you might have also guessed that, well, this is tuberculosis data collected by the World Health Organization, so there's probably a variable that corresponds to country. That, in fact, is the ISO2 variable. This is the ISO2 letter abbreviation. AD stands for Andorra. So we've got two variables in the columns. And then male, female, that's not a variable, but gender is a variable, and age group is a variable. So we have two variables that are spread out across the columns, so the age and the gender. You might notice we've got the unfortunately named females of unknown age as the FU variable. There's one other variable in here, and that is, like, what does this number represent? What is the numbers? What do the zeros and the ones and the twos represent? Well, those represent the number of cases. So we've got 5 variables here. Year and country are in the columns. Age and gender are spread across the column headers. And then finally, we've got one variable in the cells. So as you can imagine, having variables, 5 variables stored in 3 different ways is going to make this data set rather difficult to work with. So let's take a look at how we might clean that up using the TidyR package. So I'll just make the font a little bigger so you can keep seeing it, hopefully. And I'm going to use this the readr package to read in this data set. Readr, a very short pitch for readr is that it's 10 times faster than the base R functions, and it just does a whole lot of, basically it fails to do some really annoying things that read.csv does. For example, it never turns your strings into factors. It also produces what's called a tibble diff, which when you have dplyr loaded, just prints out a little more nicely. It just prints out the first 10 rows, all the columns it fits on the screen, and it also tells you the type of each column, which is very, very useful. Now what I'm going to do first is I'm going to take all of the columns that are not variables and gather them up. And I'm going to say, so I want to gather them up, well, I need to say, well, what does the column name represent? Well, the column name represents basically this demographic group, this combination of sex and age. What does the cell represent? That represents the number of cases. What columns do I want to gather together? I want to gather everything from male, ages 0 to 4, to FU, the females of unknown age. And when I run that code, I get a data frame that's much tidier. So now we have country, that is still that's a variable in a column. Yeah, that's a variable in a column. We've got demographic. It's not quite a variable, right? It's actually two variables. We have to deal with that next. And then we have count, which is also a variable. So we need to split that demographic variable apart. I'm going to use the separate function, which is also in tidyr, and I'm going to split it into sex and age after the first character. So if I do that, I now have a tidy data set. Each of these columns is a variable: country, year, sex, age, and the number of cases. Now I could, of course, do a few other little things with this. I could rename that ISO2 variable to be more informative and reorder the columns, but that's just kind of icing on the cake. It doesn't make the data any tidier. It just makes it a little easier for us humans to work with. So that was a very brief element of gather is spread. I showed you separate. There's also which uses regular expressions in a slightly different way. The opposite of those two functions is unite. So when you have a variable that's spread out over multiple columns, you use unite to join them together. And then we have some other verbs, some more esoteric types of data. Hierarchical data is the domain of nest and unnest, which you'll often get when you're working with JSON. If you'd like to learn more, you can Google for tidyr. The package is available on CRAN. There's a vignette that describes the functions in more detail. You can also Google for tidy data to read the more comprehensive paper that I wrote about the underlying theory. So that describes, what tidy data is in much more detail, and there's a few case studies that work through some other types of messy data that I didn't talk about. So once you've got your data into R, you've got it tidied, you often want to start with transformation. So you've got your data into R, you've tidied it, now you want to do some transformation. That's the job of the dplyr package. And the goal of the dplyr package really was to try and make all three of these components, all three of these challenges easier. And so the first way dplyr makes your life easier as a data analyst is it helps you think about the problem of data manipulation. And it does that in a slightly surprising way. It does that by restricting you, by saying there's actually really only 5 verbs you need for the vast majority of your data manipulation challenges. And if you combine those 5 verbs with a group by operation, that's going to solve most of your problems. So those 5 verbs are select, which allow you to pick variables by their names; filter, which allow you to select observations by their values; mutate, which allow you to add new variables, which are functions of existing variables; summarize, which lets you reduce multiple values down to a single value; and arrange, that lets you reorder the observations. So now when you're tackling a new data manipulation problem, you don't need to think like which of the thousands of functions in base R should I use. You just need to think which of these 5 functions can advance me one step closer towards my goal. I'm going to give you a little demo of these using a different data set with a story that I think is a little sad. So I'm going to use this baby names data. So this data is provided by the Social Security Administration for each year, for each sex, for each name. It tells you how many babies were born with that name and what proportion is that of all the babies born in that year of that sex. Now here we only have 5 variables, so you're unlikely to want to use select. But select basically allows you to operate on variables as if they're positions. So you can say, give me all the variables except prop, or give me all the variables between year and end. So this is really useful for large data sets. It also has a whole lot of operators that let you work with kind of the names of the variables. So if you want to select all the variables that start with something, or end with something, or contain something, or match a regular expression, you can easily whittle down thousands of variables down to the handful that you actually need. Now, so select lets you pick the variables you want. Filter lets you pick the observations you want. So for example, I could find out all of the records about Hadleys. So you can see, for example, in 1906, there were 6 boys named Hadley who were born. We can also combine these together. We can say, give me all of the babies born in 1900 who are female. Or 2013, there's a little bit of an interesting story here. You'll notice the most popular name in 1900 was Mary. About 5% of all girls were named Mary. The most popular name in 2013 was Sophia, and interestingly, only 1% of girls were named Sophia. So there's actually an interesting trend over time that names in the US have become diverse. The most popular names have fewer people associated with them. We could use mutate if we wanted to add new variables. It's sort of hard to come up with what we're interested in, but there are actually some interesting trends if you look at just the first letter or the last letter of each name. We could use a range to change the order of the rows. Here I've arranged it in descending order of proportion, so that's going to give me the relatively most popular name at the top. And so you can see in 1880, like 8% of all boys were named John, which is pretty crazy, I think. One of the most useful verbs is summarize. If we just use it on a raw data frame, it summarizes everything. So here I'm just counting up all of the total number of babies in this data set. You can see there's about 300 million. But summarize is most useful in conjunction with the group by operator. So grouping is sort of a fundamentally statistical operation. You say, what's the unit of analysis for this problem? So here I'm going to group by name and then apply exactly that same summary, and that's going to give me a count of the total number of babies with each name. And when we do that, we can see, well, it comes out alphabetically ordered. We can see some unpopular names like Arbid, and hopefully Arbriella is just a typo instead of Gabriella, Arden, Aiden, Ardish, and so on. Now, the idea in dplyr is that each of these verbs is very, very simple. So if you want to solve more complicated problems, you join them together. And I want to illustrate that with this sort of somewhat surprising finding that hopefully when you think about it, you have some pretty strong priors about how many girl Johns there are and how many boy Marys there are. So let's run that. And first of all, I'm just going to pick out the rows corresponding to John, Mary, and William. Then I'm going to group by name and sex, and then I'm going to count. And when we do that, you get something fairly surprising. So for example, according to this data, there's about 20,000 female Johns, 15,000 female Marys, 15,000 male Marys, and 16,000 female Williams. Now, I'm pretty sure this isn't just really sadistic parents. I think this is a data quality problem, that there's some data entry errors where names that should be males have been entered as females and vice versa. Now we can use that to answer another kind of sad story. We look at the Hadleys, group it by sex, count how many there are. You'll notice that there are 15,000 female Hadleys and only 1,700 male Hadleys. And if we combine that with a visualization, which is really, really common when you're doing data manipulation, you'll see, unfortunately, Hadley as a female name has just been like exploding in popularity lately. And maybe we should even make that a log scale just to see what that gives us. Yeah, so you can see there's basically Hadley as a female name is just like growing exponentially, which is rather sad for me. Now, often you're not just working with a single table of data, you might be working with multiple tables of data. So dplyr also provides a whole lot of useful verbs for those. You're probably familiar with the joins of the SQL, inner join, left join, right join, full join, and so on. I call these mutating joins because they effectively, you typically use them to add more columns, add more variables onto your data set. Another type of join that's really useful but much less well known are the filtering joins, the semi-join, and the anti-join. These don't affect the columns, they just affect the rows. So a semi-join gives you all of the rows in X that match in Y, and an anti-join gives you the opposite. It gives you all of the rows in X that don't match in Y. As you can imagine, this is really, really useful when you're joining a lot of data together, because often if you do that without thinking about it and you do a whole lot of joins, you find you've accidentally thrown out 90% of your data because there's some data quality error that prevents the tables from joining together nicely. Now, as well as those mutating and filtering joins, there's also some set operations that basically let you work with observations or rows and combine them together. Now, the other cool thing about dplyr is that it not only works with local data frames, like I showed you, and the local data frames, thanks to Romain Francois, who's a really fantastic C++ programmer, are really, really fast. You can work, I think, pretty comfortably with 10 or 100 million observations in memory with dplyr and not even have to think about it. dplyr, however, also works with much larger data sets by talking to other systems. In a database, you can basically hook dplyr up to that database, you write R code exactly the same way as if you're working with a local data frame, but dplyr translates your R code into SQL and sends it to the database, so all of that computation happens on the database server rather than on your local computer. If you'd like to learn more, Google for dplyr. There are a lot of vignettes included in the package. They basically go into much more detail on each of those topics that I covered briefly here. It's available on CRAN, just released a new version a couple of weeks ago. Still under active development, still lots of stuff to do, but I think it's a really solid platform that a lot of people are getting value for. So if anyone wanted to ask any questions now, now's a good time. I'll give you a few seconds to gather your thoughts if you're interested. Otherwise, we'll carry on and take some more questions at the end. Okay, let's go on. I wanted to talk a little bit about visualization with ggvis. As I mentioned, ggplot2 is still kind of my go-to tool for visualization, but ggvis is, I think, really exciting, and I wanted to talk a little bit about it because it's clearly the future of visualization to me. So what is ggvis? Well, first of all, it's a grammar of graphics like ggplot2. So it's the same idea as dplyr, the same idea as tidyr. The way you solve complicated problems is by joining together simple pieces. So the grammar of graphics provides you these little pieces, you join them together to create whatever graphic, a graphic that's tailored specifically to the problem at hand. The coolest thing about ggvis is that it's reactive. That means it's interactive and dynamic. So when your data changes or the parameters of the plot change, the plot updates without you having to do anything. This is built on the functional programming tools provided by the functional reactive programming tools provided by Shiny. It's a pipeline, so like dplyr, like tidyr, the way you combine pieces together is with a pipe. And finally, it's fundamentally of the web. ggvis graphics aren't just graphics you can put on the web like PNGs. They're fundamentally made with web technologies like HTML and CSS and SVG. So let's take a little look at ggvis in action with another data set. I'm just going to show you this data set from ggplot2. So one of the things that ggvis currently lacks is many interesting data sets. I'm just going to use this data set about fuel economy. If you've used ggplot2 before, the basic idea of ggvis should look pretty similar. We start with a data set, we pipe it into ggvis to create a visualization. We're going to put displacement on the x-axis, highway miles per gallon on the y-axis. Then we're going to layer on some points, and we're going to layer on some smooths. So, you know, the equivalent ggplot2 code for this looks pretty similar. There are a few minor differences, but by and large, it's pretty similar. The difference, however, comes when we add interactivity in the picture. So if we want to control the smoothness of the smooth, how wiggly it is, we can use the span parameter. And here, rather than just setting it to a fixed value, I'm going to set it to an interactive control. So I get a slider. So now when I draw this plot, I get an interactive slider. And as I change that slider, you can see the smooth updates. And the cool thing about this is there's just so little code for that. For you as the author of the visualization, ggvis understands how to update this stuff. Well, here's another example. This is possibly the most useless animation ever. This is just waggling. It's smoothly transitioning through different parameters of the smooth. You know, it's not very useful because A, you probably wouldn't want to do this, and B, even if you did, you'd actually want to know the parameter rather than just changing. But the cool thing about this, from my perspective, is that all ggvis knows about is this is a sequence of changing values. It doesn't care where those values are coming from. It just knows how to update the plot. And that means we can also do things like handle streaming data. Now, I don't have a good streaming data source, so I'm just going to make up this, this reactive data set. So rather than a data set that's fixed over time, now I have a reactive data set that changes over time. This is just a very simple simulation, and it's easier to show the results than to explain that code. So if I run it, hopefully this comes through on the webinar okay, you'll see I have a whole lot of points randomly moving in random directions at random velocities. And the graph itself doesn't, you don't need to kind of tell ggvis that the data is updating. It just knows you fed it this reactive data frame. It knows how to update the data. Now, that's not to say creating interactive visualizations is trivial, because I did have to add these 2 extra lines that set the axes of the scale. Because one problem when you create interactive visualizations, if you have to think pretty deeply about what should change. And if I don't do that, both the data changes and the scale changes, which is basically pretty awful. So important, it doesn't solve all of the problems of creating visualizations, but it certainly makes some things much, much easier. That was a quick demo of ggvis. If you want to learn more, again, you can Google for it. There's a website with lots of more documentation going into more detail what I showed you. It's available on CRAN. Again, it's not as fully featured as ggvis yet, but as you've seen, it's got some really cool features. It works particularly well in Shiny apps because it is fundamentally reactive. I think it's worth playing around with, and I'm going to be spending a lot of time, particularly next year, working to make sure that it's as good as ggplot2. Next, I wanted to talk a little bit about modeling, particularly with the Broom package by David Robinson. And I don't want to talk just about really big, complicated models, but I think it's really important also to talk about simple models, because often you need models just to make useful visualizations. So here are some data about house sale prices in Texas. We've got about 25 years of data. Each of these lines is a city. We've got about 46 cities here. Now, it's really hard. Probably what you're most interested in when you look at a plot like this is to say, well, what's going on in the long term? And that's really hard to see here because there's 2 problems. So first of all, there's this really strong seasonal effect. That basically there are more houses sold in the summer than there are in the winter. And that's a known phenomenon that's not that interesting if we're looking at long-term trend. The other thing that makes it difficult is that obviously bigger cities like Houston, which is this line, for example, have many more houses for sale and sold than smaller cities. So it's difficult to interpret the long-term trend, both because of the seasonal difference and because we have this difference in the intercept, that some cities have many more houses that are being sold each year. So I'm going to explore that and see if we can do a little better by using some models. So again, I'm going to load this data. I'm going to get rid of a couple of entries that are not good, the overall total, and this, the data for Palestine, which is very, very noisy. Just recreate that plot I just showed you. This one's a little bit messier. I'm not sure why that is. But what I'm going to do is I'm going to get rid of that seasonal pattern by fitting a model. Now, there's lots and lots and lots of ways of deseasonalizing data, but I think one particularly compelling way that not enough people know about or talk about is using models. And here I'm going to fit a model. I'm going to predict the log sales based purely on the month. Now, this is not a good model, but I don't really care about this as a model. I'm just going to use it as a tool. I'm just going to look at the residuals from this model. So for each city, I'm going to fit this model and look at the residuals. I do that, and then when I plot that data and look at it, and here I've overlaid an average on top of those the somewhat noisy individual cities. Now we can get a pretty good sense of what's going on in the long term. You can see this gradual increase up until the housing crisis, a big drop. We've got some weirdness happening around 2010, some big ups and downs, and then sort of a gradual recovery from then until now. The model's really important here, so we can subtract out that seasonal trend, we can subtract out the intercept, and we can see across all of these cities what's the common pattern. Now, if you're doing a real data analysis, of course, you probably want to go and look in a little bit more detail on some of these outliers. Why was there a huge drop here? Are there cities that don't follow a different trend? That's all interesting stuff to know, and that you could then, you're in a good position once you have this data to dive into answering those questions. Now, there I just used the model as a tool. I fit it, took out the residuals, and immediately threw it away. Now, it's also useful to do other things like, well, there's lots of other things we could do. And so here what I'm going to do is save that model. And I'm going to use a verb I didn't talk about before that comes from dplyr called do. So do is kind of a generic verb. It allows you to do anything. And in this case, it allows us to create a column, which is the linear model. Now, this sounds a little bit crazy at first. It sounds a little crazy. Here I have a data frame. One column in that data frame is the city. The other column is for each city, we have that linear model. Now, it took me a little while to get my head around this, but I think this is actually really useful because it allows us to keep the models tightly coupled with the sort of the model level covariates, like the city in this case. What I'm going to do next is use one of the functions from the from the Broom package by David Robinson called glance. What glance does is for each, I'm just going to make this a little wider, and I'm going to use a fewer decimal points. Put that out again. So what glance does is it extracts the model level summaries from each of those models I fit. So now for each city, rather than having a model object, I have the R squared, the sigma, the t-stat, p-value, and so on. And so now I have that. I can plot that. You know, if I actually cared about this model, this would be really important to look at, just a dot plot of the R squared. So even though I'm not really interested in this as a model here, I'm just using it as a tool, it's still interesting to see some of those cities fit pretty well, an R squared of 0.4, so there's clearly some sort of strong seasonal pattern there. Whereas other cities like McAllen and Harlingen fit very, very poorly. So, you know, if you're going to think about this model, you'd obviously want to explore those cities in more detail, figure out why they're not fitting so well. It's a really, really useful technique when you're dealing with large. If you'd like to learn more, unfortunately, you can't just Google Broom. That's a little too generic. You'll need to Google Broom R. You can find David's website, which explains much more about how it works and talks about many of the different model families that it works with. I wanted to finish off by talking briefly about big data and R, because I think it's a topic that's of interest and concern to many people. And since I'm talking about big data, I think it's sort of my privilege and my obligation to come up with my own definition of big data. And to me, big data is data that can't fit in memory in one computer. And these days, that basically means data that's bigger than 5 terabytes. And I think that's a really important threshold because as soon as you start storing your data on disk or spreading it in memory across multiple computers, the programming challenges become much, much, much harder. Now, a step down from big data is medium data. That's data that fits in memory on a server, so 10 gigabytes to 5 terabytes. Dealing with medium data is challenging. It's not as challenging, but it's really important to take advantage of all of the cores in the computer. And then finally, for small data, that's data to me that fits in memory in a laptop. And that's just, as long as you have reasonably efficient algorithms, it's really easy to write code that works with small data. And I think, this is what R is fantastic at. R provides, in my opinion, an unparalleled environment for exploration and rapid prototyping of small data. Now, in principle, there's no reason that R also couldn't work with medium-sized data, but that means that a lot of people need to learn a little bit about how multi-core programming works and take advantage of it in their packages. There's no technical reason why that can't happen. It's just a matter of time, I think. But what about big data? R just isn't that suitable for big data. But to me, that's not actually a huge problem. Because first of all, I'd say like 90% of big data problems are actually just a matter of finding the right small data. So if you can get the right small data through either some creative combination of subsetting or subsampling or summarizing, often getting that right data set allows you to solve the problem you're interested in. So, maybe all of the data you have is really, really big, but to answer a specific problem, you only need a small data set. You need the right small data set. Now, of course, that's not easy because the first data set you pull down is going to be a small data set, but it's not going to be the right small data set, so you need to think about how to get to that as quickly as possible. But, I think that's a big subset of big data problems are the right small data. Now, another set, I think, is just where you have a very, very large number of small data problems. This is the sort of problem where you want to fit a model to like, millions of people. Each fitting a model to one person is easy. All the data fits in memory, but you have millions of them, so that's going to be challenging. This is sort of the domain of Hadoop and similar systems. And then finally, there is definitely a subset of problems where you do actually need all the data, the irreducibly big problems. Now, to me, I think R is actually pretty good at getting you to the right small data. As I mentioned, dplyr helps you with this because it allows you to write R code to get that data. That avoids you having to do this expensive cognitive switching between R and SQL. If you have to use SQL to pull the data down and R to figure out if you've got the right data, that's going to be quite slow because you have to constantly switch between R and SQL. And that's not hard because R and SQL are so different. It's hard because R and SQL are so similar, but with a few really important minor differences. R, I think, is okay at dealing with these lots of small data problems. You'll need to talk to some other system like Hadoop. There are some R packages like for each and repay and R Hadoop that help you with that. I think one of the really big challenges here is that you need to make sure that the way you've stored your data kind of matches the statistical problems you want to answer. Ideally, the data is split up in such a way that each computer has a subset of interest so that when you solve these lots and lots of small data problems, the data is already split up as you need it and you don't need to do a lot of moving of data around, which is very, very expensive. Finally, these irreducibly big problems, R is never going to be the right solution for this. People are going to write these in programming languages that are designed to optimize performance of the computer, not to optimize the performance of the human. People are writing these typically in C and C++ or Fortran. Scalar is becoming increasingly popular these days. The main thing here, I think, is that R needs to be able to talk to those systems. So you have packages like Spark R, which I think are really great first steps. There's still a lot of work to be done. R, in my opinion, is a really good environment for talking to other programming languages because that's part of the fundamental original design of R. John Chambers' original vision was R as this glue language to help you talk to different programming languages like C and Fortran. So I think R is great at this, but the potential, by and large, is still not been taken advantage of. But hopefully in the future, we'll see more people doing interesting things in that today. So to finish off, my goal here is I want to create a fluent interface in R for data analysis, an interface where you spend your time, your precious cognitive energy on the specific data analysis problems, not fighting with R to get it to do what you want. The goal is to create tools that become invisible with time. I want these tools, your use of these tools, to get to the point where it's like touch typing. You don't even really think about it, and R code just kind of naturally flows out of your fingertips. Now, there's still lots and lots of work to do here. R is far from perfect, and I certainly don't want to give you the impression that I think it is perfect. There's still lots and lots of work to do. I think R's modeling tools are fantastic. It's an incredibly rich, diverse ecosystem. That diversity is also a challenge because there can be a lot of differences, unimportant differences between different packages. And I think particularly the connection between modeling and visualization is really interesting for people to explore. So I just wanted to finish off by showing you this, one of my first slides again. I strongly believe that, like in the age of Google, one of the most important things you can know is the name of something. If you know the name of something, you can easily Google, find out more information. If you don't know the name of something, it's really hard. These are the packages that I've worked on. Again, I'm not perfect. I don't claim these packages are perfect, but I am working really hard to provide you this really seamless and fluent interface in R. I hope you find these packages useful. If you do have problems with them, please let me know. I'm always interested to hear about things in R that just seem like too hard to do, that they should be much easier. Thank you. The Plier package, I think it is still, like it's not going to go away, but equally I'm not going to be working on it much in more detail because I think basically, I think the the way I think about it is I think Playa does a really good job of solving a set of problems that most people don't have. And dplyr is just sort of a refocusing of Playa exclusively around data frames, which are the problems that most people have. So dplyr is definitely the future. It's like, for some problems, it's like 10,000 times faster than Playa. My experience from talking to people is dplyr is also much, much easier to learn because you have to sort of understand the split, apply, combine idea before you can take advantage of it. Now, split, apply, combine, I think, is really, really useful tool to have in your toolbox. But equally, if you don't have to think about it like you don't in dplyr, it's really nice not to have to think about that. And another question from Michael about Python. I think, and whether or not it's sort of a complement to R, my experience talking with data science teams in many different companies and many different industries is that the vast majority of data science teams use both R and Python. Sometimes that there's people who, are 99% of the time in R, and other people who are 99% of the time in Python. Sometimes it's teams where everyone is sort of 50-50 R and Python. I think it's great to have that, like when you get stuck, if you get stuck in R or if you get stuck in Python, it's really great to have that complementary tool so maybe it's easier there. Now, personally, my job is to try and make R as awesome as possible. I spend my time exclusively in R because what I want to do is make sure that, you can do everything that you need to in R while absolutely accepting the fact that most people are not going to do everything in R. They're going to use a mix of languages, whether that's Python and R, or R and JavaScript, or C or SAS or whatever. That there's always going to be a mix involved. And I think that's great. I just focus exclusively on R so I can have as much impact as possible in that one area.